Hello and welcome to session 2 of the Aircraft Design Workshop by SimScale in collaboration with the IAA Design Build Fly competition. My name is Anna and I will be your presenter for today's session. And before we get started, I just want to make sure my sound is working okay. In the GoToWebinar application that I'm using, you'll see a button that says raise your hand. And if you can hear me, can you please raise your hand right now so I can make sure the sound is good? Great. So I see some hands going up, so I think the sound is good to go. So in session 2, we're going to talk about structural simulation in aircraft design. And to start, we're going to start with a very important topic. What is finite element analysis? This will form kind of the basics for the structural simulations that we're going to talk about later in the session. We're going to talk about wing bending and torsion. After we talk about finite element analysis, we're going to talk about structural analysis types, static, dynamic, linear, nonlinear, what's the difference, and when should we use which analysis type. Next, we'll do a live demo. So this is where we'll go into the SimScale platform, and I'll show you a project that we've done, how to set up a wing bending and torsion simulation in SimScale. Fourth, we will talk about the homework for this session. So we like to provide homework so you get a chance to do something hands-on and use the SimScale platform to get a better understanding of how the platform works and how you can use it to improve your designs. Finally, we'll do a question and answer session. So at the very end, feel free to write any questions you have into the chat and we'll go through those at the end. Okay, let's get started with what is finite element analysis. And so finite element analysis is a computerized method, and it helps us to predict how real-world objects will react to forces, vibration, heat, etc. And so basically what it is it's a way to virtually test designs, structures, etc. And so for example, if we look on the left, we see aircraft brackets. And what we can do is we can see how these will respond under extreme loading and vibration conditions. And we can do this virtually. We can visualize the stresses all on a computer and get an idea of which design might be the best. So let's take this a little bit farther and talk about the equations that are behind the finite element analysis code. And so to start off with, we might have a simple cube, and if we pull on it with a force, it will deflect by a certain distance. And so if we have something simple like a cube, we can easily use our constitutive equations. And so these equations basically relate surface area force to stress and strain based on the stiffness of the material. And so this is quite easy to do when you have something that's square. But for example, if we have something that is a hook or a bracket, it's not so easy. It's an irregular shape. And so what the finite element method is doing is we can basically break down this object and we can relate the stiffness to the displacement to the force. And I'm sorry, actually on this slide there's a bit of a mistake. And so displacement is U, stiffness is K, force is F. And so how do we do this? And so these are basically the steps of the finite element method. The first thing we have to do is we start with a continuous body. So we have this hook. It's a continuous solid, and it has a load applied to it, a distributed load. The first step in the finite element method is to break down this hook into smaller elements. So we have elements, and each element consists of 4 nodes in this case. And then the loads are applied directly on the nodes. And in FEA we have different element types. So we have 1D, 2D, and 3D elements. And they're useful for different things. In SimScale, we're doing 3D modeling, and so we have For FEA, we have 4-noded tetrahedrons, and we have 10-noded tetrahedrons. And the main difference is kind of the resolution, and so we'll see this later in the demonstration, but especially for bending, it's good to use the 10-noded elements because you'll get better results. So this is just something to keep in mind. Obviously, in this case, you have more nodes, and so the computation might take longer. Your mesh will be bigger, but it will give you better results. After meshing, the next step is to define the material model, and so this will basically affect how the structure behaves. It depends on the stiffness, it depends on the density of the material. So some examples are steel, aluminum, iron. Later we'll see an example using balsa wood. So it's really important to define the correct material to get to understand the behavior better. And now let's talk about material behavior. So there's two types. You have linear elastic, you have a linear elastic range, and you have a plastic range. And many of you have probably seen this stress-strain diagram in your engineering classes, but it's important to note this when you're doing a simulation. You need to know what range the material is in. And so under smaller loads, you'll have your material in this linear range, so the stress and strain it's a linear relationship. But once you hit your yield strength, you come into the plastic range here, and you no longer have a linear relationship. So more and more load, you'll see less displacement. And the final step is solving. And so that's what this equation shows. We can invert the stiffness matrix and multiply it by the forces to solve for the displacement vector. And so we're solving for the displacements at all of these small nodes within the model. And then you get results. And this slide, it basically is showing that it depends on your mesh. Your results, the resolution of your results will depend on the mesh that you're using. And you can really see this in this example. This blue zone is much larger compared to here. And so basically your mesh size will directly affect your results. So that's a short introduction to what FEA is. Now let's talk about FEA specifically in SimScale. So today we'll talk about the structural analysis types that are available in SimScale. So some types are linear static analysis. This is the most basic type. This is a lot of times when you first learn about FEA, this is what we're talking about, linear static analysis. So you have a linear elastic material, loads are applied slowly, there's no extra vibration or anything like this in the structure. Next is nonlinear static analysis. So this can happen when you have nonlinear material behavior, you have high bending, things like this. And then dynamic analysis, which has some subcomponents of modal, frequency, and harmonic analysis. And so dynamic analysis is especially important in terms of maybe impact. So if you have something dropping, maybe like even landing of the plane, this is really a big impact, and so you're going to see kind of inertial and vibrations induced into the system that you won't see with normal static analysis. And so let's talk a little bit in more detail about the difference between linear and nonlinear. And so with linear, the relationship between the force and displacement is linear. The material is always in the elastic zone, so you typically will have lower loading, and it's only valid in terms of small deflections and rotations. So if you have a very large bending, as in like a plane wing, you'll have kind of a large bending in this case, so you can't use a linear analysis. Nonlinear, the relationship between the force and displacement is nonlinear. The material, for example, can be in the plastic zone, and this is material nonlinearity. You have large deflections, for example, and this can really relate to things such as moving parts, composite materials, rubbers, impact loading, things like this. The next is the difference between static and dynamic analysis. And so static, as I said a little bit earlier, it refers to when a model is kind of loaded slowly. So we're slowly applying the load so we can ignore the inertial forces and damping. And in this case of a static analysis, we only need a single time step. This time step can be broken down into intervals. You know, you can have a 1 second broken down into 0.25 intervals, but generally the whole thing can be computed in one time step. For dynamic, the loads are applied as a function of time. And then some examples here are shock, vibration, seismic loading with earthquakes, and things like this. So this dynamic analysis is typically more complicated, but it can be, in some instances, much more realistic than static analysis. And so for our session today, we're going to talk about nonlinear static analysis. So as I said before, we're going to have a look at an airplane wing. This is subject to large bending. And so in this case, we would want to use a nonlinear static structural analysis. So let's have a look. Right now we'll do a live demonstration, so we're going to go into the SimScale platform. But before we do, I want to show you the load cases just so you can see them a little bit better. I think it's easier to see it on the slides. And so the first case that we're going to talk about is bending. And so if you see the wing here, this end is fixed. We fixed the end of the wing, so this is the part of the wing that's close to the body of the plane, and then the load for bending is applied to the bottom of the wing. It's a pressure load, so it's an upward load on the bottom of the wing, and this will induce bending into the structure. You'll see the end of this wing bend upward. The second case that we're going to talk about is torsion. And so with the torsion load, you see we have kind of a twisting, and so again, the wing at the root is going to be fixed, and then there's a pressure load on the top of the wing, an upward load on the top of the wing in the front, and then a downward pressure load on the bottom of the wing in the back half. And so this will induce twisting into the wing. Okay, so these are the steps we're going to go through: pre-processing, simulation, and post-processing. And now I'm going to switch into the SimScale platform. Give me 1 second. So here is the project that we've done. And I'm going to open it and go into the SimScale workbench. Okay, so now the project has opened and we can see the wing that we're going to have a look at today. So this is the CAD model that has been uploaded onto the SimScale platform. And the first step after uploading is we have to mesh. And so if I go here, this has already been meshed. We've already completed the mesh on this project, so I'm just going to show you what it looks like in the setup we used. And so if I go into the operation, we're using TET meshing, and so this is an automatic algorithm. There's also manual. Manual is optional here, but automatic is it'll automatically create the mesh for you. You don't have to input very many parameters. We've selected a moderate mesh, so you can see it's kind of a moderate fineness here. And as we talked about earlier in the session, this is a second order mesh. We know there's going to be bending in this structure, and so we want to make sure that that's accurately captured. So we're using a second order mesh, and what this means is that each of these tetrahedral elements that you can see, if I zoom in, you can't see the nodes here, but they exist, and so each of these elements has 10 nodes associated with it. And it looks like there's one question I'm just going to answer really quick. It says, is there any 3D geometry check available before meshing? And the answer is yes. So when you upload a model to SimScale and you try to do a mesh, if there's any issues, you're going to see it in this mesh operation event log. If your solid has an opening or any sort of defect, it will give you a warning, and so you can check your model before setting up the simulation. Okay, so after the mesh is ready, this shouldn't take too long. I think maybe 10 minutes to do this mesh. The next step is to go to the simulation designer, and this is where we set up the simulation. So the first run that's done is the bending load, and the second is the torsional load. We'll look at both right now. And what I like to do is, just to see it better, you can switch from surfaces with wireframe to surfaces here. So then you can kind of see the structure better and where to apply the loads. The first step is basically deciding on the analysis type. And so in this case, we're doing a static analysis. We're assuming that the load is applied slowly to this wing. There's going to be no additional vibrations and things like that. So we don't need to do a dynamic analysis. And then in this case, again, since there's a lot of bending, or we're expecting to see larger bending, we're going to set nonlinear analysis to true. This is typically set to false, so you have to be careful and make sure that this is set to true before setting up the simulation. Okay, so after we pick an analysis type, the next thing that we need to do is pick a material. And so in this case, we've chosen balsa wood for these small light planes. This is the normal material because it's very light and it's very stiff. And so you can see that the material has been assigned to this whole volume, the whole volume of the wing. And in this case, we've selected it's a pretty low Young's modulus, but this is the Young's modulus of balsa wood and the density. And again, we're kind of simplifying this. We're assuming it's a linear elastic model, so we're staying in this linear range. Okay, the next thing after setting up the material model is we need to set up the boundary conditions. And so the first thing we can do is, in any FEA model, the model needs to be fixed. As you can see, I mean, if you don't fix a section, it's floating in space, and so you're going to get rigid body motion is what it's called. So in this case, we are fixing the end that would be attached to the body of the plane, so the wing root is being fixed. And in this case, fixed value, so it can't move in any direction. The X, Y, and Z direction, the displacement is set to 0. And the bending load is applied on the bottom of the wing. So the whole area on the bottom of the wing has a pressure load applied to it. And this is kind of where the nonlinearity comes in. You can see that the pressure is applied as a function of time, and so what we call this is it's ramped. And so in this case, since we know there's going to be large bending, we need to apply the load over a series of time steps. If we apply it just on one time step, it might break the simulation, and so we apply it in 4 time steps, which we'll see in the numerics. So every 0.25 seconds, we're applying, we're multiplying this load, and so it's gradually ramping up the load. And so the final load on the bottom of the wing will be 1,500 pascals. And so this comes into play in simulation control. We can see that we've selected an interval of 1 second with an initial time step of 0.25, and so this is what I mean with the ramping. So the load will be first multiplied by 0.25, then 0.5, then 0.75, and then 1. So by the end of the simulation, this entire pressure load will be applied to the bottom of the wing. Okay, and so once this is all set up, the final step is to run the simulation, and we can see right here that the run time took about 28 minutes. So this is a relatively quick runtime. And the nice thing about SimScale is, you can set up this simulation, this bending load simulation, and let it run, and at the same time you can be setting up your second simulation, which is the torsional load. And this can easily be done by just duplicating the first simulation setup and then changing the load conditions. Everything else stays the same, so the material stays the same. This fixation constraint is again the same here, fixing the root of the wing, and then the only difference is you can see right here the upper and lower torsional loading. And so on the top we are applying a pressure of 2,000 times time, 2,000 pascals times time, and on the bottom the same. So this will give us the twisting motion of the wing. And the runtime is exactly the same. And so now we've seen the simulation, we've seen the mesh, we've seen the simulation setup, the run has finished, and so now we can go into the post-processor, and this is where we view our results. And so for wing bending, we can go to solution fields, and this can take a second to load. It depends on the size of the simulation. I hope this one should be pretty fast. And in the meantime, while this is loading, I can answer a few questions. So let's see. One question from Tomas is balsa wood really isotropic? And the answer is no. I mean, we have to make some assumptions in this case because wood is an orthotropic material, which SimScale does not currently support. So we've made some assumptions on the behavior of the wood, etc. Let's see. Another question is, can we import pressure loads from a CFD analysis? And the answer there is also yes. You'll see under pressure that it's possible to upload a table, and so you could take your forces that you get from your CFD model and upload those as a CSV file onto SimScale in a structural analysis and directly apply those loads to your wing. Okay, so let's have a look at the results. And one thing that we can do is to actually see how the wing is bending is use a filter. And so the first thing I like to do is change the initial state of the wing to a solid color and then provide some opacity so it's a little bit lighter. Okay, so now we can add this warp by vector filter. And so this allows us to see the bending of the wing. And another thing we can do is change this instead from a solid color to, for example, von Mises stress. And so we can actually see the stresses in the wing, as shown here. We can scale it, and then you can see the von Mises stress shown here. And so you have to check, from what I've read, the yield strength is 25 megapascals. And so here our maximum is showing 29 megapascals. So you'd have to take a look at if the wing is yielding and where. And you can see here that obviously the highest stresses are near where this wing has been fixed and in this section of the wing. Okay, so this is the bending. If you want to see it slightly more extreme, we also have this scale factor that you'll see. So 1 means that this is the actual, you're viewing the actual displacement, the actual deformed wing, but you can also increase this because in some cases you'll have very small deflections and you might want to increase the scale factor. And so, for example, you can increase it to get a better visualization of how it's deforming. Okay, so that's the first one. Let's have a look at the solution fields for the torsional load. Okay, let's give it a second to load. I have another question that I can answer. If the wing is constructed from different materials, how can I assign each material to each part? And so what you can do if you have multiple materials for your wing, what you would want to do is you'd have to create separate volumes because as you can see, if I quickly go back here to the material, you're assigning the material based on volume. So if you have 2 different volumes, you can connect them using a bonded contact in this contact section. And then you would be able to separately assign the materials to different sections of the wing. Okay, so let's have a look at these results. The default here is the displacement. We can see it's deflecting about 0.013 meters, or twisting. That's the maximum displacement. Again, if we switch this to solid, we can get an idea of how the wing is deforming in this torsion state. So there we can see it. It's a little bit hard to see when it's scaled on 1, so we can maybe increase this to 4. To see it a little bit more clearly. So you can see it's a little bit different. It's deflecting more in the back than in the front, as we would expect for torsion. Okay, so that's the basics of how to set this up in SimScale. You can see the results. You can see different results here: Cauchy stress, displacement, nonlinear strain, von Mises stress, etc. So I'm going to switch back again to my presentation. So we went through these steps: pre-processing, simulation, post-processing. And just to do a quick wrap-up, so with mesh generation, in this project we did a automatic tetrahedral mesh. We used second order because we knew there was going to be bending and large deformations. Next, for the simulation setup, we did a material definition. We assigned the material as balsa wood. We applied the boundary conditions, fixed on one end, and then pressure loads for the bending and torsion. And then we ran the simulation, and it took about 28 minutes. And then finally, we went into the post-processor to see the results. We could see the initial undeformed state and the deformed state of the wing, along with the von Mises stress and displacements. And then I have some nice images of the results. We kind of saw these in the post-processor already, but we can see displacement, so the undeformed shape versus the deformed shape. This is in bending. And the von Mises stress, so we see the highest stresses obviously here in this kind of center I-beam. And so this might be an area that we want to make thicker. If we realize that the von Mises stress is too high, we can thicken this, and it will increase the stiffness so our wing does not fail. One more view, and now we switch into torsion. We can see the largest displacement is here at the tip, at the end. And there's a twisting in this wing. And so those are the post-processing results. And just a small comparison, we can see the bending, the stresses are a little bit higher. There's more deflection here as well compared to the torsion. Okay, so that's the main part of the session. Now I'd like to switch to the homework and question and answers. I see quite a few questions popping up, so we can go through those right now. Or let's talk about the homework and then we can go through the questions. So please keep writing questions if you have them. So for your homework, your task is to do something very similar to what was shown to you in this live demo. Your task is to investigate the stresses and deflections in a wing when applying a bending and torsional loads due to wind pressure. And so we provide you with the wing model. If you have your own wing model that you would like to use, that would also be interesting to apply the loads and see how your wing performs. So this is an option as well. You will find all the resources for the step-by-step exercise, the recording, and the homework at simscale.com, Aircraft Design Workshop. We will also send out an email. This session is being recorded, so you'll get a recording of the session and the homework. And remember, this is the second and final session. So there was a first session covering CFD. This session was on FEA and structural analysis. If you submit both homework assignments for those sessions, you will receive a certificate for completing this workshop and attendance. And just so you can see the homework quickly, the homework is in our forum, so it's already been posted. You will get an email tomorrow with the link to the recording and the homework, and you can start it here. It has a very nice explanation of the loading and all the steps that you need to set up the simulation. Okay, so I think that is it for the session. Let's have a look at questions. A question from Octavian: does the number of cores influence the meshing, except taking longer with less cores, of course? It can. It depends on the size of your mesh. In some cases, you'll have a memory error if your mesh is too large and you're not using enough cores. This is kind of, it depends on the case. It depends what kind of mesh you're using. It depends how many elements, how many nodes you have. So I mean, in this case, since we knew we were doing, the mesh is not so big, but since we're using second order elements, we decided to go with 8 cores. And so this can be very dependent. For FEA types of meshes, typically you need less cores than you would need if you were doing a CFD analysis. Those can sometimes take up to 16 or 32 cores. So this is kind of experimental. You know, if you try to run a mesh and it's taking too long, or you get a memory error, then you just need to increase the number of cores, and your mesh should be fine. It doesn't actually influence how the mesh looks, though. It just affects the speed and sometimes memory if you don't have enough cores. Okay, let's see. So this user wants to know what kind of materials are available on SimScale. In SimScale, we have a material library, and so this has your kind of very most common and basic materials, so steel, aluminum, rubber. So these kind of materials are available in SimScale. If you have your own material, you can always upload it. I can show you right now on the platform. So if you go to materials, you can see, especially for nonlinear materials, it's possible to upload your parameters, upload your stress strain curve with a CSV file. And so you just need to upload it as a CSV file and let SimScale know which separator you're using for the file, and then the stress strain curve can be directly uploaded into SimScale to work with your material. This question is, can we do a temperature-dependent analysis in SimScale, and how can we implement the temperatures? Yes, in SimScale, I mean, this is an option. If you go to analysis type, right now we're using a static analysis, but you can see in SimScale, solid mechanics is not the only thing that we have available. We have fluid dynamics with all of these different analysis types, solid mechanics with these static, dynamic, modal, and harmonic, and then we have thermostructural. So this includes thermomechanical loading. So this thermomechanical, you can apply thermal loads as well as structural loading. Okay, and Faizan asked, how do we optimize our simulation design? So that's what simulation is great for. You can upload an initial design, a design that you think will work, and you can see how that design behaves, and then you can compare it to different designs. So if you think that in this case, with a wing, maybe you notice that the stress is not so high and you think you can reduce the weight, so you can take material out of the wing to actually lighten the structure. But you can really see, when the structure will fail using virtual testing. And it's very quick. You can upload 3 or 4 models and test all of them and see which one performs better under the loading that you're using. Okay, let's see. Jayant asks, how do we do an FEA analysis of the whole aircraft body since it's freely suspended? Doesn't it become a rigid body? And yeah, the answer would be yes. In FEA, you typically don't need to do the whole structure at once. It's actually better to take a look at parts of the structure, and yes, like you have to fix a certain part of the structure so it's not just floating in space. Otherwise, you will not get valid results. Muhammad asks, can I use SimScale to test the gluing material on a surface? The answer would be yes. I mean, if you know the material properties of any material that you're using, then you can test it in SimScale. Muhammad also asked, can we perform a parametric study in SimScale? The answer is yes. So as I said, I mean, SimScale is only a simulation tool, so you would have to use a different CAD tool to change your designs. But as soon as the designs are changed, you can easily upload them and run the simulations. As I said, once you have the simulation set up, you can just keep making copies, and it's very quick to set up different iterations for different designs. Let's see, there's some more coming in. Can we use the same results for UAV designs? I mean, you mean the same process? I would say yes. I think this is really relevant to any sort of UAV design that you're working with, this kind of FEA analysis. Nikhil asks, is there an option for creating localized meshes? I'm not quite sure on this question. Can you maybe explain it a little bit more, Nikhil? And then Mohammed asks, can we perform a vibrational study? And yes, that is possible, Mohammed. Again, this is under your analysis type, so you cannot perform a vibrational analysis when you're in static. But if you switch here to dynamic or harmonic or modal, you can have a look at the vibrations. Ah, okay, yes, I see. So Nikhil wanted to know is, can we refine our mesh in areas with higher stresses? And yes, that's true. So again, if we go to the mesh, in this case, we did a very simple automatic mesh, but even so, we can add mesh refinements. And so if we know that there are going to be areas of high stress, we can click on Add New, and it will add a mesh refinement. So you can change the mesh in specific areas on specific faces or volumes depending on your results. And it's always good to really check the mesh. This is called a mesh convergence study. So to start with a coarser mesh and see how refining the mesh changes the results, because ideally you want to get to a point where you have a good enough mesh. You don't want it to be you don't want it to take up too much computational time, but you want to have accurate results. So you kind of have to find that balance. Tristan asks, is it possible to view the effects of bending and torsion at the same time? If you mean in the post-processor, in the SimScale post-processor, we only have one screen, so you would have to view one at a time, but if you use ParaView, it's possible to actually have two screens available to see them at the same time. Another question is how to visualize the action of the bending, like in a video. Let's see if we go here back to the post-processor. In this case, we can actually see the steps. So let's see. If we click play, we can watch this like a video. So it will show the frames and how the bending is occurring. If you want to create a video with the animation, this currently cannot be done in SimScale, but basically what we're using in the back end here is ParaView, and so you can see get ParaView. This is a local version of ParaView, and in ParaView you can create these animations in MP4 format, so it's like a video. Let's see, can you suggest good texts for FEA analysis for beginners? I can suggest, if you have been on our website, it's called SimScale Academy, we have an Introduction to Computer-Aided Engineering course, and within that course we provide lists of good FEA books and CFD books. So have a look at that and to get some ideas. Okay, I think that answers all the questions. So I thank you again for your time. Thank you for joining this session. I hope you enjoyed this workshop. And as I said, you'll be receiving an email with the homework. If you have any questions, feel free to reply to that email and I can answer them. So thank you again for being at this session, and I will talk to you later. Bye.